Hints on how to construct a final diagram for a simple two-body process A plus B goes to C plus D. We first have to decide whether this can be an annihilation process in which the two initial state particles annihilate into a gauge boson. In that case, the form momentum transfer will be equal to the total energy momentum. If they cannot annihilate, they must exchange a gauge boson in a scattering process. In that case, the q squared of the process is equal to the difference between the final particle form momentum and the initial particle form momentum. Now we must decide which gauge boson can be exchanged. First of all, we have to remember that at each vertex, quantum numbers are strictly conserved. So, first of all, baryon and lepton numbers must be conserved, and if we're not talking about weak interactions, also the particle flavor. Now we must consider the charges at each vertex. If the charge of the particles is not zero and it doesn't change at the vertex, we can exchange a photon. If the particle weak isospin is not zero and the charge doesn't change, we can exchange a Z. If the charge does change by plus or minus 1 unit, we can exchange a W plus minus. And finally, if the color is not zero and the color does not change at the vertex, we can exchange a gluon. So here's the first example. The process E plus E minus goes to U bar. We clearly cannot couple the electron directly to the U quark, so this is an annihilation process in which the E plus E minus annihilate into a U bar pair. This can proceed via the exchange of a photon or a Z, because the electron and positron and the U bar both carry electric and weak isospin charge. Cannot go via the exchange of a gluon or a W, because the E plus E minus does not carry color and the charge does not change at the vertex. The second example is the process E plus E minus goes to neutrino-antineutrino. Unless the neutrinos are electron-type neutrinos, this is again an annihilation process. It proceeds via the exchange of a Z boson. Cannot proceed via photon exchange because the neutrino doesn't carry electric charge, and neither the electron nor the neutrino are colored, so gluons cannot be exchanged. The charge is not changing at the vertex, so that W plus minus exchange is also excluded. The third example is the process E minus U goes to nu ED. In this case, it must be a scattering process because the electron cannot directly couple to the U quark. We will in fact exchange a W minus boson because the charge changes by 1 unit at each vertex. This is possible because both the electron and the U quark carry weak isospin. We cannot exchange a photon because the charge changes, neither can we exchange a Z. And since the electron and the neutrino do not carry color, we cannot exchange a gluon either. The next example is the decay of a D quark into a U, E minus, and an electron antineutrino. To conserve baryon and lepton number, we must connect the D quark to the U quark and the electron to the antineutrino. This means that at each vertex, the charge changes by 1 unit and we can exchange a W boson. We cannot exchange a photon because the charge changes. Likewise, we cannot exchange a Z. And since the electron and the neutrino don't carry color, we cannot exchange a gluon. Our last example is a red U quark scattering off a blue D quark, giving a blue U quark and a red D quark. This is clearly a strong process since it involves color exchange. Since strong interactions conserve flavor, we must connect the two U quarks and also the two D quarks. That means that the two vertices are connected by a gluon of a red anti-blue color such that the color is conserved at each vertex. We cannot exchange a photon since the color changes, neither a Z nor a W boson since all of these cannot change the color of a particle.